To form a thin magnetic field that can trap ions around a sphere, we can use the concept of a magnetic mirror field configuration. This configuration involves creating a magnetic field that gradually increases in strength as the distance from the center of the sphere increases, effectively reflecting the ions back towards the center and confining them within the region. Let's consider a coordinate system with the origin at the center of the sphere. We can assume that the magnetic field is axially symmetric, meaning it depends only on the radial distance from the center. We'll denote this radial distance as r. The magnetic field can be expressed in terms of its magnitude b, r, and its azimuthal angle dependence. To simplify the explanation, we'll assume the azimuthal dependence is uniform, meaning the magnetic field has no preference for any particular direction around the sphere. The magnetic field configuration we desire is often referred to as a mirror field, which can be achieved using a combination of dipole and quadrupole magnetic fields. For the sake of mathematical simplicity, we'll focus on the dipole field contribution. The magnetic field due to a magnetic dipole moment can be expressed as B r equals Greek letter mu 0 for Greek letter pi 3 m r r 5 m r 3, where B r is the magnetic field at radial distance r. Greek letter mu 0 is the permeability of free space. M is the magnetic dipole moment vector. Comma denotes the dot product. R is the position vector of a point in space. To create a mirror field configuration, we want the magnetic field to be stronger at larger radial distances, gradually decreasing towards the center. This means we need the first term in the equation above to dominate over the second term. To satisfy this condition, we can choose the magnetic dipole moment vector m such that its direction is opposite to the radial position vector r at each point. This can be written as m equals Greek letter mu r, where Greek letter mu is a constant related to the strength of the dipole field. Substituting this expression into the equation for B, R, we get B, R, equals Greek letter mu 0 for Greek letter pi 3, Greek letter mu r, r 5 plus Greek letter mu r 3, equals Greek letter mu 0 for Greek letter pi 3, Greek letter mu r squared, r 5 plus Greek letter mu r 3, equals Greek letter mu 0 for Greek letter pi 2 Greek letter mu r 3. Notice that in this configuration, the magnetic field is inversely proportional to the cube of the radial distance, which causes the field to increase as r decreases. By adjusting the constant Greek letter mu, you can control the strength of the magnetic field. You can choose the appropriate value of Greek letter mu to create a magnetic field that is strong enough to trap ions around the sphere, but not too strong as to cause them to collide with the surface of the sphere. Please note that this is a simplified explanation using a dipole field contribution, and in practice, more complex magnetic field configurations are used to achieve better trapping efficiency and stability. Additionally, higher-order field contributions such as quadrupole fields are often employed to improve the confinement properties. The actual design and implementation of a magnetic field trap require careful consideration of various factors and may involve additional mathematical techniques beyond what we've discussed here.